Hi everyone. So we are going to use the idea of z-scores to introduce the normal model. So a few hundred years ago, a French mathematician, I'm not going to try to say that name, showed that for many unimodal and symmetric distributions, approximately 68% of data will have z-scores between -1 and 1. 95% of the data will have z-scores between -2 and 2, and 99.7% of the data will have z-scores between -3 and 3. So you can see, just based on these percentages, it's going to be really rare for you to have a z-score above +3 or below -3. So this rule is called the 68, 95, 99.7 rule, or also called the empirical rule. About 75 years later, a very, very famous mathematician named Gauss came up with the formulas that created the model for this. And we call this the normal model, or sometimes called the Gaussian model. So I have a picture of the normal model here, and you can see that it shows the mean, which is the z-score of 0, right in the center. And then a +1 would be 1 standard deviation away, or 1 z-score away. A z-score of 2 is 2 standard deviations above the mean, and a z-score of 3 is 3 standard deviations above the mean. And then a -1 is 1 standard deviation below the mean, -2 is 2 standard deviations below the mean, and -3 is 3 standard deviations below the mean. And then you can see the 68, 95, 99.7 rule pictured in this model. When we write the normal model using z-scores, we call this the standard normal model. And we have a notation for this. And if you're ever doing your homework and I ask you to describe the model, I'm not looking for a sentence. I'm looking for this right here, this notation. This describes the model. It tells me that's a normal model. That's what the capital N stands for. The first number is the mean, and the second number is the standard deviation. So in the standard normal model, the mean is 0 and the standard deviation is 1. So we don't have to talk about the normal model in terms of z-scores. We can apply the normal model to any distribution that is unimodal and roughly symmetric. And I want to emphasize right here that you do not need to convert data values to z-scores in order to use the normal model. And the reason I'm going to emphasize that is because your book, Help Me Solve This, even some tutors might tell you that you do. And I'm telling you right now that you don't. We use z-scores to compare data values from different distributions, but we do not need to convert things to z-scores in order to apply the normal model. So in this picture of the normal model, you can see that instead of using z-scores, I've labeled it with mu and the standard deviation. So remember that mu is the mean. So I have the mean right in the center. And if I take that mean and add the standard deviation once, then I come up to this value here. If I add the standard deviation twice, I come here, and 3 times up here. Same thing if I subtract. So if I subtract the standard deviation once, I'm here, twice I'm here, and 3 times I'm down here. And now I have that empirical rule again, where it says that 68% of the data will be within 1 standard deviation of the mean. 95% of the data will be within 2 standard deviations of the mean, and 99.7% of the data will be within 3 standard deviations of the mean. So each of these percents represents a likelihood of observing a data value within that region. So I would say that I have a 68% chance of observing a data value within 1 standard deviation of the mean, or a 95% chance of observing a data value within 2 standard deviations of the mean. This percent also represents or corresponds with the area under the curve, and I'm kind of pointing that out for the math majors in this class. If you're going on to take Calc 2 or Calc 3, you're going to study the area under the curve a lot. So I want you to notice that the area under this curve represents 100%, and that I know that 68% of that area is within 1 standard deviation of the mean, and 95% of that area is within 2 standard deviations of the mean, and so on. So again, this mu represents the mean, and sigma represents the standard deviation. And then we have the general way of describing a normal model, where we use the capital N to say that we can use the normal model. And the first number is the mean, and the second number is the standard deviation. So before I move on and do any examples with the normal model, I kind of want to make sure that we're really clear about talking between observed data and predicted data, or modeled data, because I find that a lot of students get mixed up with what we did in Chapter 2 with what I'm talking about now. So back in Chapter 2, we were summarizing data. So we were looking at tables, and those tables represented a sample, and they were a sample of observed data. They were data that we measured in the real world. And we took that data and we graphed it. We made a histogram or a stem and leaf diagram or a dot plot, and we described the shape, and we discussed whether or not the mean or the median was the best measure of the center, or the standard deviation or the IQR was the best measure for the spread. And we used our calculator to calculate statistics. And we saw that X bar represented the mean and S represented the standard deviation. But now we are talking about a model. And a model is, it's an ideal, right? Models allow us to predict what we're going to see in the world. So these are predicted values, not observed values. And these models represent a population. So when we're talking about a population and we're talking about the mean or the median or the standard deviation, we don't call those statistics anymore, we call them parameters. So statistics if it comes from a sample, but parameter if it comes from a population or a model. And we use Greek letters like mu and sigma to describe these parameters of the population, so that, you know, when we're writing something really quickly, we can just use this symbol and then everybody knows that we're talking about a population instead of a sample. It's important to know that every model has a specific set of conditions that must be met before you can apply that model. In the case of the normal model, we know that it needs to be unimodal and roughly symmetric. Those are the conditions in order to apply it. But every model has their own conditions. And you want to remember that models will never match observed data exactly. Sometimes they'll get really close, but they won't ever match up completely perfectly. Nothing's ever perfect in statistics. But models are really nice. I mean, they're nice because they allow us to make predictions about data, to talk about data with the idea of the likelihood of observing something, and to be able to say that a data value is remarkable or not. So I'm going to just do one example in this video, and then I'm going to do more examples in future videos. And with this example, I'm going to specifically use the empirical rule. So it says some IQ tests are standardized to a normal model with a mean of 100 and a standard deviation of 16. So I drew in all the information with my 68, 95, 99.7 rule. So I have the mean at the center, that's the 100. I added 16 to get the 116. That's the first standard deviation away. I added 16 again to get 132. That's 2 standard deviations above the mean. And then I added 16 one more time to get 148, and that's 3 standard deviations above the mean. Then I subtracted 16 once to get 84. That gave me 1 standard deviation below the mean. 68 is 2 standard deviations below the mean. And then I subtracted 16 3 times and got 52, which is 3 standard deviations below the mean. Which means that 68% of IQ scores will be between the scores of 84 and 116. And 95% of IQ scores will be between 68 and 132. And then 99.7% of IQ scores will be between 52 and 148. So we're going to use this rule to answer the questions A through D. There are some people that like doing these questions this way. If you don't, the immediate thing I'm going to show you next is how to use your calculator to do this. And you're going to find that your calculator is much more efficient. But your calculator also allows us to talk about values that aren't directly on 1, 2, or 3 standard deviations from the mean. So looking at part A, it says about what percent should have a score between 100 and 116. So remember that 68% of the scores are between 84 and 116. And the normal model is perfectly symmetric. So this 100 is directly in the middle of 84 and 116. So if I divide this 68% by 2, I'll have my answer. So 68% divided by 2 is going to give me an answer of 34% of scores should be between 100 and 116. For part B, it says what percent of people should have a score above 116. So I'm looking here, and I want to find the score above 116, all the way above. Well, again, I know that the normal model is perfectly symmetric. So kind of looking past this rule, I know that 50% of the data has to be above 100 and 50% of the data has to be below 100. So if I know that, it's really hard to draw. So if I know that above 100 is 50%, so I know that above 100 is 50%. I just calculated that between 100 and 116 is 34%. So if I want to find the difference between that, so if I want to find this amount, the amount above 116, then I'm going to take 50%, subtract 34%, and I'll get the answer of 16%. For part C, it says what percent of scores should, or what percent should have scores below 68. Let me erase my previous marks here so that we don't get them mixed up. Okay, so below 68. So now I'm looking here, and I want to know what percent is below 68. Well, I know from the 68, 95, 99.7 rule that from here to here, from 68 to 132, is 95% of the data. And I know that the entire model represents 100% of the data. I also know that the normal model is completely symmetric. So if the whole thing's 100%, and the middle between 68 and 132 is 95%, then I have 5% left over. And since I have 5% left over, and the normal model is symmetric, then I must have 2.5% above this 2 standard deviations and 2.5% below the 2 standard deviations. So this answer here is 2.5%. For part D, it says, in what interval would you expect the central 95% of scores? So it's right on my model. I don't have to do any work, but I included this question because I wanted you to listen to the wording of it. So it's asking for an interval, and it's asking about the central 95% of scores. So not the lower or the upper, but the central 95% of scores. So that's what the model shows me, that this central 95% of scores are between 68 and 132. So I'm going to write that in interval notation and write 68, 132.